of whole plane SLE.
Thank you. I would like to thank the organizers for the kind invitation to this nice place and very nice meeting. And thank the former speakers who mentioned some non-rigorous work. Yeah, I'm sorry. Thank you. Better? Is that better? Yeah? Okay. Okay, so I'm going to speak about a generalized notion of multifractality of whole plane SLE for a certain version of whole plane SLE, but I'm going somehow to follow the path we followed to get there, and I might be a bit fast at the beginning if I want to reach the generalized notion of multifractality. And so it starts with a study of the SLE as a case study for holomorphic functions in new disk, and in relation to the what is called the Bieberbach conjecture. So you take f, which is a holomorphic function, and injective. So then you have a1 different from 0, and the famous Bieberbach conjecture stated that a2 in modulus was smaller than 2a1 in modulus. And actually, of course, it was proven, and the conjecture is that it was valid for any level n. And actually, it was guided by the intuition that the Kuber function, which is a bijection between the unit disk and the complement of a half line, actually should be extremal for that conjecture. And finally, it was proven, so it was a famous problem. It was proven in '84 by Debranche. Actually, it proved another conjecture, which actually there was a string of conjecture made in between, and there was one which was implying this string, and finally Bieberbach, and this is the way Debranche proved it. But actually, before that, one important step was the proof by Loevner that actually A3 in modulus is smaller than 3A1. And actually, this is where I invented the Loevner map. And of course, we all know that Schramm revived Loevner's method in '99 by introducing randomness in the Loevner map. And you know, this is the SLE. So the idea actually of my collaborator, Michel Zimsmeister, some years ago was to take the whole plane SLE in a version which is unbounded and try to see what you could say about the coefficients of this map in respect to this Bieberbach conjecture as in a kind of case study. So the version I'm going to use is this one. So you are in the unit disk, you have the SLE equation. So the source term will be typically, essentially the usual one on the boundary, which is exponential of I square root of kappa bt. But actually we discovered on the way that a lot of properties were valid for Levy-Loevner processes. So you could, instead of bt, you could take a Levy process LT, which has usually a characteristic form, which is the expectation of the exponential is given by some Levy symbol eta of psi. And in particular, if you take eta of psi to be kappa divided by 2 psi to the alpha, with alpha between 0 and 2, then this corresponds to the Levy symbol of an alpha stable process. And of course, SLE corresponds to Brown motion, so alpha is equal to 2. So just mentioning it is not going to play a role very much in the talk, but the first results we got were actually valid for LLEs, for Levy processes too, so we just incorporated them. But of course, you could always think of eta of psi when it will appear in the beginning as a kappa over 2 psi to the 2. Of course, here I put a kappa, which is totally arbitrary because I want to make contact with SLE later. So this is so how does it look like? Well, you have the unit disk, you have your source term lambda of t, you have the point 1, and you have this map from the interior of the unit disk to the complement of the SLE curve. So at time t, you have a tip, gamma of t, which is the image by ft of lambda of t. And actually, when times grows and times flows, actually you erase this curve continually. And when you let the time go back to 0, you have the full curve starting from the tip gamma of 0, which is the image by f0 of 1, because the source term starts at 1 at time 0. which was written here. And of course, here f of 0 is fixed, so at any time the image of the unit of the origin is the origin here. So this is the setting we use. And so of course everything is moving, so actually there is a nice result, which is that if you take your Loeffner map, multiply it by, renormalize it by exponential minus t, expand it as a power series, then the coefficients an of t you get here actually are by conjugations equal in law to the value at 0. So the conjugate all plane LLE that is valid for the Levy processes too. So the conjugate of ft by this operation has the same law as f0. So it means that an of t multiplied by this is the same as an of 0 in law. So there is something which plays a role, also important role in the Bieberbach literature, which is what is called the odified version of the map, which consists in taking the ft at z square and taking the square root. So if you want to have the right holomorphic branch, you divide by z square and just remultiply by z here. And that one, so the conjugate of this odified one, obeys a similar conjugation law of this type, which is in law the same thing as h0 at time 0. So meaning that the coefficients you have, of course this map here is expandable on the odd powers of z, and so the coefficients are called b2n of plus 1 of t, and those coefficients, once multiplied by this oscillating factor, actually are in law the same things as the value at time 0. So actually, I'm just mentioning this because to say that there is a dynamics in this, but we are going to be interested in the values at time 0 of the map, and are going to look at the expectations of those coefficients, knowing that there is this nice dynamics underneath. So, so again, I recall that you have to rescale by exponential of t here, and once you do this, you expand the Loeffner equation on S power series on both sides, and you identify coefficients, and of course you get recursion equations for n greater than 2, which are this type. This is the Loeffner's method. So you have, so the coefficient of order n, this derivative in time, a dot n, and an itself are related to the former coefficients for lower indices k from k from 1 to n minus 1. And of course, lambda bar here is just a source term, which was either this one or that one for the general Levy case. And of course, lambda bar, the conjugate, is just inverse of lambda. So this is the starting point. I'm not going to spend much time on this. This is the way Loeffner proved the inequality for A3. Actually, we put the proof in the first paper, just as a reminder. And so the first kind of results we got that were by looking at expected coefficients. So if you have, so you write an, which is the value at 0, b to n plus 1, which is the value at 0, and then you have this kind of results, which are not difficult to get, which tell you that the expectation of those coefficients are typically given by products of explicit expressions. And the nice thing is that they are nested. You see, when you get to the higher one, the expectation of an is the exponential expectation of an minus 1 multiplied by the next coefficient of order n minus 2. Yeah. So of course, if you look at that and try to make some of these factors 0, you are going to get identities. So this is not really deep, not difficult. So you get, for instance, if you decide that eta 1 is 3, then you will find that in expectation your map, the derivative of the map will be given by a simple formula. This is valid, eta of 1 equals 3 is valid for kappa equals 6, because remember we had this kind of, so take alpha equal 2, take eta of 3, and then for kappa equals 6 is going to be 3. So this is the first case. So if you decide that you want to have eta 1 equal 1, eta 2 equal 4, that is enough. That stops the whole coefficient. The next ones higher will be 0, and then you have this kind of easy result, which is valid for, this is actually, if you give yourself these two conditions for a Levy process by the Levy-Khinchin formula, you can show that actually that is only SLE2 already. So there is not, it's not broader than SLE2. And if you take eta 1 equal, eta 1 equal 2, for instance, in this formula, you are going to, in the last one, you are going to stop the coefficients for the b's, and then you will find that the modified version of your Loebner map in expectation for the derivative just given by this simple formula. And this corresponds to SLE4 in particular. So there were other calculations by Kampainen 5 years ago about for expectations of there were some overlap with those, but he was looking at slightly different things, like looking at the first two coefficients and higher moments. Right here we have the first moment for the time being for all the coefficients. But the surprise came when we looked at the expected square coefficients. So for instance, expectation of an square. So for SLE6, so you go from n equal 1, which is always 1 by construction, and then you let n go up, and then you see that you have all of these curves as a function of kappa, and you see that for kappa equals 6, they all go through 1. Okay, so you go higher. This was for n equal 8. You do it numerically higher, and you have more curves, and they still go through kappa equals 6. So this is you have all of these expectations for a number of n's, right? Again, these are the indices up to 8, here up to 19 for n, and they of course vary with kappa. But for instance, you observe a peculiar property for kappa equals 6, which of course is kind of conspicuous, and you would like to understand it. And you do the same thing for the you divide by n, say, you explore a bit, and you see that you draw them as a function of n again, so they are the same data. And then you see that for kappa equal 2, they all pass through 1. And then you do it again. So you were at n equal 8. Don't do it by hand, okay? It's not going to work. I will tell you where you can do it by hand. It's really n equal 4, to say that you stop. And so you go up to 19, and you know they still go, the expectation of n squared in modulus divided by n, just they all go through nicely through 1 for kappa equal 2. Okay, so clearly you have a conjecture, and you start calculating, and so this is what you expect. This what we just saw for kappa equal 6, this one, for kappa equal 2, that result. You calculate A4, say, A3 square, A4 square, you get this kind of formulae, and nicely, if you put kappa equal 6 here, you are going to find 1. And so this is a proof. So of course, so we did it by hand, computer assisted, formally, and then numerically up to 19. So the theorems are the following, finally, that and actually that is valid for LLEs. But eta 1 equals 3, you have this, that includes SLE6. Eta 1 equal 1, eta 2 equal 4, you get this one, SLE2, and this one, eta 1 equal 2, then you get this formula which includes SLE4. This is for the modified version. Okay, so the good way to do it is actually to look at other quantities, which are the derivative moments, which of course will be later linked with the integral mean spectrum. And so you have this kind of result, which is if you take the single moment of the derivative to some power p, you will get this simple formula. If you take now the modulus of it to the power p, you are going to get this different formula. And this is not valid, of course, for any p, but it's valid only for a special set for a given kappa, for a special set of exponents, p of kappa, which are given by this formula. And then the alpha here and the beta here are given by this explicit formula in terms of kappa. So actually, I put here the name of Lutsenko and Yermolaeva because they developed similar results here, and they even proved a slightly stronger result just in this case for eta 1 equal 1. That was enough to have this result, but this was a specific derivation. So their method is different from the one we use, but I'm not going to go into the details here anyway. So I'm going to tell you later from where these kind of things come from, and briefly. But of course, if you assume this result for the time being, you take kappa equals 6 now. For say the case, so this is general. Of course, for a given kappa, p of kappa can be any number here. But if you decide that you would like to have the second moment, because the second moment, of course, is going to give you access to the second moments of the coefficients, then if you require P to be 2 here, you get two cases, either 6 or 2. So for 6 and 2, you get what we had before here for single moments, and you get also this kind of simple formula. So once you have this simple formula here, or Z1, it's easy to re-expand and get the results I was mentioning for the AN square, right? This one's kappa equals 6, and this one kappa equals 2. Okay, that could just come from the explicit forms. Anyway, so that was somehow the tip of the iceberg, and but more so I'm going to. But so this was so we looked at here clearly at the moments of the derivatives. So clearly these quantities are related to the multifactor integral mean spectrum, as we saw in 2 talks today. But I'm going just to somehow enlarge the study by looking at for the moment logarithmic moments. So logarithmic moments, they are just such that, so you would like to expand the log of f now. So there's also a famous problem linked with the Bieber-Black conjecture. So if you want to do that, a good way is just to look at the logarithmic derivative of f, so which is given by this kind of quantity. So we have this kind of results now that if you take the same whole plane SLE kappa at time 0, then it has some special logarithmic moment of this type, so not any p, but this one for a given kappa, where you have this kind of closed form also. So again, see, if you want to have that exponent here to be 2, well, that corresponds to kappa equal 2. And in that case, you have this corollary, which is that the expectation of the second order moment of the logarithmic derivative of f naught is given by this closed form. So of course, if you have this, you can look at the expansion of the log of f naught over z in terms of the z's. So you have these coefficients gamma n, and in expectation, the moduli of the gamma n's squared are going to be given by 2 over n squared once you have this form. Right. So, but of course, once you, so here the motivation for looking at this kind of quantities was coming from the fact that we wanted to study the logarithmic, the log of the map. But once you do this, of course, there is no reason to stop, and you can ask yourself, what about the generalized moments, mixed moments of this type? So f prime of z to the power p in modulus, and then f naught of z in modulus to the power q. Okay. So if you do this and use the same techniques, which I did not describe yet, you are going to find some other results. So for instance, you are going to find one particular case, which is when you take p equals 0 here. Sorry, p equals 0, so you forget about the derivatives, and then you just look at the moment over the q. So for a special value, for a given kappa, again, there is a special value of q such that you have a closed form, and which is given here. So which is f naught divided by z to that particular power of for a given kappa is given by this particular form in terms of kappa again. Okay. So always the same thing. This is just the modulus of 1 minus z to some power, and this is the modulus of 1 this is 1 minus z bar. So the distance to the disk, this is the distance to point 1 to some power. Okay. So clearly there is a structure, and so now we have somehow the general theorem for all of these moments, which is this one. So mixed moments. So actually you can look at moments moduli at a point z, but you can take second moments at 2 different points. That's really the same thing. You are going to get it in the same way. So you can actually disentangle z and z bar, take z1, take z2, take first moment of the type f prime to the p over 2, f of z1 to the q over 2. The z1 to the q over 2 are just for, they are convenient. You have to put them, but of course they get out of the expectation, so they are just spectators. And then you have the conjugate of the same moment at point z2. So they are going to be given by, again, by a closed form of this type, depending on powers gamma here and beta here. So of course, if you take z1 equals z2, you are going to get this expression, then this expression. Beta is always kappa over 2 gamma square. And then, of course, it's not valid for any p and q, but it's valid for a special set of parameters p and q, which are actually sitting on the parabola. in the PQ plane. So this parabola, so actually the exponent gamma here is given simply in terms of 2p minus q over 1 plus kappa over 2. So, but of course, it's not for any pair of parameters p and q, so it's not for any gamma. So it's only if p and q are related in certain way, which is given by this quadratic formula. So you substitute gamma here equal 2p minus q over 1 plus kappa over 2, you put it in this, and this is the equation of quadratic, and actually it's a parabola. Okay, so only on those parabola you have this kind of closed forms. And so that looks like this. So here I drew, so PQ plane now, so I drew the cases, so these are the parabolic curves PQ sub kappa. So for kappa equal 2, this is a blue curve, kappa equal 4, the red, and kappa equal 6, the green. And you see, so you see the intersection of, for a given kappa, say, let's take the green, for instance, kappa equals 6. It intersects q equals 0 at p equals 2. And this p of kappa in general is given by this formula, which is the formula we had in this former result, earlier result, this p of kappa here, which was telling you that you will have closed form for the moments, for some moments of the derivative, so it corresponds to q equals 0. And if you now look at we had this result here for p equals 0, now for some special value of q in terms of kappa, that corresponds to the point which is intersection of p equals 0, which is this point here, say this point here or that point here, depending on kappa. These are the points where you are going to have these closed forms. But if you give yourself a kappa, say kappa equals 6, you follow the parabola, and along all of these parabola, you have this closed form result. Okay, and of course, it explains the p of kappa we had before. And if you want to have some result for the derivatives, of course, the logarithmic derivative. In that case, the two moments p and q are equal. So you try to see, if you want to see if you can get this result, well, that corresponds to intersecting for a given kappa, so the corresponding parabola with the straight line where q equals p. So you draw a straight line and you see where it intersects, and then you are going to get your logarithmic moments. Okay. Okay. So this was somehow the motivation for the spectra, and so the technique we use is simply the theory actually, which was set up by Belyaev and Smirnov in 2005 when they studied the integral mean spectrum of the SLE, of a certain version of the whole plane SLE, and so they derived a certain differential equation for f, which was given by the expectation of f prime naught to some power p. Okay, that was the technique. So they have this equation. I'm not going to use all the details here. The f r and f theta are the derivatives vector r and theta. This is in cylindrical in polar coordinates on the unit disk. Actually, their version of the whole plane SLE was the external version. So it was a map from the exterior of the unit disk to the domain, to the plane slit by the SLE. So it was just the different version. In our case, we map the interior of the unit disk to the domain slit by the SLE. In their case, they were mapping the exterior of the unit disk to the plane slit by the SLE. Okay, that is going to be important because we are going to see the difference later. So actually, the difference is reflected in the fact that there is a certain term here, sigma, which in their case is +1, in our case is -1, and that is going to give you different kinds of solutions, and in particular, the existence of these closed form solutions in our case, not in their case. And we are going to understand it later, to understand why later. So I'm not going to dwell much on all the details, but lambda here is the generator of the Brownian process, which is driving the Loevner equation. But in the case of the Levy process, you just replace lambda by the generator of the Levy process. And actually, a good thing is just to rewrite this equation in terms of holomorphic coordinates. So just you switch to z bar variables. You define your f of z bar as the expectation of the product of the two, and then you write down your equation in terms of z and z bar, and defining the derivative with z bar S d bar. So if you do that, the same equation can be recast in this way. Well, that is the case of the moments. Of course, you have to do the same theory. If you want to have the PQ moments, you generalize this approach to the PQ moments, and then you have a slightly different equation, which involves not only P, which is the moment here, but also Q, the moment of F naught. I mean, meaning, if you want to study not only these derivative moments, but those guys, you have, of course, to work a little bit and look at the new equation you get. Okay, so just I want to mention, physicists like very much to work with Z bar, and they usually consider them as two independent objects. And this is the right way to look at things here. And this is why if you work with Z and Z bar and consider Z and Z bar as independent, as Z1 and Z bar, Z1 and Z2 bar, everything passes through, and then you can get these results for moments at different points. Because I have recast all the results in terms of results at a given point Z, but actually when you take moduli, you can really split things into two terms and have your result for pairs of conjugate points Z1 and Z2. Okay, so everything goes through. So anyway, without going into the details, you look at the algebra generated by this kind of functions, phi of Z, phi bar of Z bar, P of Z Z bar. You try to see what happens if you take rotationally invariant P of Z Z bar. If you do that, you have a nice algebra. Everything, somehow factorized. You have a lot of calculations to make, and you're able to get your results, including the general Q case. But so that was for somehow a way to access. So of course, when you have these kind of expressions, phi alpha 1 minus Z to the alpha, P of Z Z bar 1 minus Z Z bar to the minus beta. Of course, you have things which are furiously looking like this kind of guys, of course, and this is what you study. And if you do that, you are going to be able, in particular, to get this general theorem, which is for the generalized version of the Belayev-Smirnov equation, meaning that you do have this kind of exact closed forms, along this special parabola, depending on kappa, where gamma is simply given by this expression in terms of 2p minus q. Okay, so I'm going to switch to the integral mean spectrum. I was a bit fast because I didn't want to stay too much on this part, but if you have questions, it's a good point. So the integral mean spectrum, so you have seen it this morning. You have the integral mean spectrum for a conformal map is a real function defined on R by the lim sup of the log of the integral of the modulus of f prime on, here we are in the unit disk in the interior, so you take R less than 1 and you integrate on a circle inside the unit disk. You take your moment to the p's power and you look at the way it diverges when you approach the unit circle. So you look at this kind of logarithmic ratio, and you call this integral mean spectrum. Of course, if you have a random map, you have in a stochastic setting, then you define the average integral mean spectrum by putting the expectation here, and that's what we have done. So to be honest, we don't have results, almost surely here, far from that. So so we are going actually to look at average integral mean spectrum in the sequel. So this is the usual definition. And here I just recall the results that you have seen in particular in the talk this morning by Gwyn of the integral mean spectrum for the bulk of SLE. So you have this function here, which is a bit complicated, but it's explicit. This is the spectrum for the bulk of SLE. There is a linear part to it, which is p minus certain value, a certain constant depending on kappa. And so that gives the average integral mean spectrum for at least for p positive. So the beta 0 bar of p and kappa is given, actually that's a result by Belayev and Smirnov of 2005. It was mentioned 2009 today, but of course it was in the thesis by Dmitry Belayev in 2005. So this is why I put this date here. Actually, we had a similar result with Binder in using a different technique of reverse SLE martingale for the chordal SLE, which is not published, unfortunately. And of course, there is the almost sure result by Green, Miller, and Son, which we saw this morning. And I should just, so the result by Belyaev and Smirnov is that beta 0 bar is either beta 0, that function beta 0, when p is between 0 and p star of p star 0 of kappa, and becomes a linear part, it becomes a linear spectrum of slope 1 when p is greater than this p0 star of kappa, which is given by this number. So this is a result which is valid for the average integral mean spectrum. This morning in the talk by Gwyn, you saw you had this beta of p, and then at some values which he did not write because they were out of the screen, they would have been out of the screen. He said that you would go to some linear behavior, and that is valid for the almost sure spectrum. If you take the average one, on the left we'll see what happens later, and on the right, when p is too high, you go to another linear slope, which is p given by this value. So this is the one we are going to see in the rest of the talk. So slightly different from the almost sure spectrum in that case. So this is a result for p. Let's say here I'm working for the moment for p positive. There will be something else for p negative later. Okay, so the claim that we have in this first paper was that the whole plane SLE kappa in our version, from the interior of the disk to the exterior, actually, and we looked at also at what is called M-fold transforms, which are just the iterations of these modified maps, which is F0 of the M to the M to the raised to the power 1 over M, and you take the proper holomorphic branch by dividing and multiplying for M greater than 1. So all of these guys have average integral mean spectra that exhibit a phase transition. So this is a claim here. I have not stated exactly what is proven or not, but and in average, so average even. So we claim that actually the spectrum will be either the beta 0 spectrum of Belyaev and Smirnov, this one, or that new function, which will supersede the other one, as we'll see a bit later. If you just start, looking at the M-fold transforms and look at the spectra, then they change slightly. They change. So you start with 3p, 2p. In general, this is given by this expression, and then you have to take the max of the Belyaev-Smirnov spectrum and these expressions. So if you take the first one, which is the one of the most interest for the time being, the first one, beta 1, has a transition point at a certain value of kappa, which is given by called p star of kappa, okay, which actually is smaller than p star of 0 of kappa, where you had this transition to the linear spectrum, right? So you have this beta spectrum, then you would go linear, but before that you have a transition. And I mentioned here the name of Lutsenko and Yermolavieva again because they have a similar result here, but by different method and on a different set of points. So they have this result for a discrete set of points in the plane from a totally different approach. So it's kind of complementary to the results we have. Let me skip this. Let me show you the map, the picture first. So that would be beta 0, the Belyaev-Smirnov spectrum for p positive here. And as I said, but you remember it's given by that formula here. So clearly for p too big, it no longer exists. So it cannot be valid for large p. So this is exactly what happens here. You have this blue branch, and then of course there is a parabolic singularity here, and you stop. But before you stop, in principle, you go to the straight line, which was at this p0 star. But before that, even there is this phase transition with a green line. So you have this beta of p, which is underneath for a while, and then suddenly it supersedes the blue one, and then you jump to this one. So this is a phase transition here at this p star of kappa, and which was this, which has this kind of expression. Okay, so this is why the spectrum here for the standard whole plane SLE map is given by the max of the two. Just one thing, you remember there was a special point, P of kappa, where we had this closed form result, right? Which was given by this, I'm sorry, I'm going to go backwards for a while. Yes, here. It was this, for this particular value of P, you had this closed form. When you have this, of course, you do read the value of the beta spectrum because just the exponent of your singularity in 1 minus z bar, right? So the beta spectrum is here, and that is given by that formula here. So for that point, you know exactly the value of the spectrum. So if you look at where it is on those curves, that we have here, well, actually it's just here. So you have this P of kappa here, you compute the value of beta, it's exactly sitting on the green curve, of course. Okay. So somehow these closed form results were already telling you that you could not be on the Belyaev-Smirnov curve any longer. You could not be you could not be clearly on the blue one. Actually, you are on the continuation of the Belyaev spectrum, you know, after the singularity. So you are on the dotted red line, and you are not on the straight line, which was tangent to the blue spectrum, the one which is the correct average integral mean spectrum for the version of Belyaev-Smirnov. Okay, so so in terms of rigorous results, what do we have up to now here? We have the following here. So we have that the average integral mean spectrum of the unbounded whole plane SLE. So again, this is valid for the map from the interior to the complex plane slit by the SLE, right? As a phase transition at P star, a special point at P kappa, where you start first up to P star with the Belyaev-Smirnov spectrum, then you go to this spectrum for a while. So we could prove it between P star and a certain number, which is the mean of 1 plus kappa over 2 and P of kappa. This is just for technical reasons here, but typically if kappa is greater than 2, this guy doesn't enter into the game. So you really have the result from P star to P of kappa. So it means for kappa greater than 2, you have the result from here to here. So you do prove that this is a valid spectrum. For after P of kappa here, we have only lower bounds, upper bounds. So we know that this expression is greater than the actual spectrum. And if you have this intermediate point for kappa less than 2, say you have this mean which is smaller than P of kappa, then we have a lower bound in this case. In that case. So just to say a few words of what you do, you first see that actually when I say the BS solution, I would say the Belyaev-Smirnov approximate solution, which they use to establish the spectrum by sub and super solution. So we really follow that technique, but we can see that for our version of the whole plane SLE, somehow there is a breakdown of the approach, and then we can work out the details of that spectrum. So you know there is a first approach which is looking at sub-solutions, super solutions, meaning if you call P of D your differential operator, you know, looking at when for test functions it is positive or negative and some annuli. So we do all of this approach, which is parallel to their approach. We use the same trial functions as they did, except that for our spectrum we use simpler test functions, trial functions. But then if we want to really establish a spectrum, then we have to go back to their method and actually use it in kind of extended way and introducing something which is hidden here, which was a duality in the gamma parameter space. So there is a technical aspect to it, and if you do that, you are able to at least prove the spectrum in certain domain. Okay, so I might have been a bit fast, I don't know. I just, but you know, it's not. It's really, so if somebody has a questions, I wanted to arrive at the last part, but might have been a bit too fast. But anyway, you have first, for any kappa, you have a set, on the parabola, you have a set of exact closed forms, right, for these moments. So here, of course, here I'm speaking of the integral mean spectrum. So I'm speaking of, what I'm speaking about here at the moment is really concerning the standard integral mean spectrum for the moments of the derivative, okay? And that corresponds to the first results we had before, which were for these kind of closed forms. And in the middle of this spectra, we have recognized where this P of kappa was, and actually it plays a kind of pivotal role when you look at the proofs of the integral mean spectrum. Now, we have seen also that there are some other results for the mixed moments, where you introduce the F naught, not only the F prime naught. And if you do this, we have seen these logarithmic moments. We have seen the general result, which is a parabola, which is that you have those kind of exact closed form results for the mixed moments, provided you are on those nice parabola. So I'm going to call them red. They are all of different colors here. The red one was corresponding to kappa equal 4, but whatever. In the sequel, this parabola, it depends on kappa, but for a given kappa, I will call it the red parabola. Okay, so on this parabola, we know exactly the mixed moments. Okay, so, but the rest here was for the standard moments. And now I'm going to look at the generalized moments. Oh, sorry, forgot to mention this. If you remember, I insisted on difference between our version of the whole plane SLE and the one by Belayev and Smirnov. If you look at their version, there is something hidden also, which is there is actually a hidden spectrum, a hidden phase transition, but actually which was safely recovered by something which is called the tip spectrum. So this is the part of the spectrum which is to the left of 0 for P negative. If you do that, this is the Belayev-Smirnov spectrum, the beta 0 here. You have the famous beta tip, which we are going to see a bit later, which is a red curve, which corresponds to the fact which has been mentioned this morning and this afternoon, which is corresponds to the fact that there is a contribution of the tip of the SLE, which is added to the bulk integral mean spectrum. So this is also a result of Belayev-Smirnov. So somehow when P is less than 1 minus 1 minus 3 kappa over 8, the red spectrum supersedes. So actually there is a hidden green spectrum here too, which is given by this formula. But so this one actually does supersede the blue one, but when it supersedes the blue one, the blue one has been superseded by the red one, which supersedes the green one. So you never, if you allow yourself to look at the tip, you are not going to see the green one. But if you discard the tip, you are going to see the green one overshooting the blue one also on the other side of the spectrum. And we are studying this with Dmitry Belayev and Michel Zinsmeister in a current work. So let me now go look at the generalized integral mean spectrum. So of course you just look at your moments, and you look at the way those moments could actually diverge when you approach the boundary of your unit disk. So you take the expectation of this mixed moment for P and Q, you integrate on the circle of radius r less than 1, and you look at the divergence here of this expectation in terms of r when r goes to r1 by lower values, and the exponent will a priori depend on P and Q, and you call it the generalized integral mean spectrum. Clearly, if F is bounded, nothing is going to happen with and bounded away from 0, and bounded from infinity, nothing is going to happen. So you are going to have the same spectrum. But here we have a version of the whole plane SLE which goes up to infinity. So when Q is going to be negative, there are some possibilities that the spectrum will be changed. Okay. So we were interested in looking at those spectra. But a first remark, so you could say, well, this is, you want to look at the spectra, and this is not what the people usually do. But actually, this is a proper formalist to encompass, in particular, the other cases, like, we'll see that later, but like, for instance, the exterior Belayev-Smirnov whole plane version. Because if you do this, you put yourself outside of the unit disk in D bar, you take the U invert, so Z is 1 over zeta, 1 over F. If you do this and compute your moment, if you take the standard moment of this inverted map, which is a standard Belayev-Smirnov map, if you do this, you are going to find easily that is given by the expectation of our version of the whole plane SLE for moment P and 2P, Q equal 2P. Okay, So it means that the standard integral mean spectrum at P for Q equals 0 for the exterior whole plane map coincides with the generalized PQ integral for Q equal to P. Right? So it means that if you look at this set, you are also going to get access to the standard map for Q equal to P along this straight line. This is one result. If you look at the m-fold transforms, you know, which is f of the m to the 1 over m power, if you calculate the derivative, that's trivial, you calculate this, you look at the mixed moments, fm prime over fm pq, well, that's easily written in terms of f prime of the mp, f of the m to this power. And of course, when you integrate on your circle to look at integral mean spectrum, you are going to make many terms, but it's going to be m times the same thing. So your spectrum here can be read off from this one, which is the standard map. So it means that the spectrum of the m-fold at the value p and q is going to be given by the spectrum of the non-transform map for p. P doesn't change, but q is just shifted to p plus q minus p over m. Yeah. So it means that if you compute one spectrum, you are going to get all your m-fold spectra by this affine map. And the case we had before, the one I mentioned here, the inversion case, just corresponds to m equal minus 1. Normally these m's are positive integers, but if you generalize it with inversion, then you can take any value on z star, and then you are going to have also the same formula. And so the m-fold spectra, standard spectra for q equals 0, will be given by this generalized spectra for a certain qm. So you don't need to know all the details, but just want to say that's a natural setup for all of these transforms. Anyway, so now what could you expect? Well, so again, so what do we want? We want to know for the whole plane SLE, okay, what could be this beta of PQ for in the whole plane PQ, okay? And we already know it for Q equals 0. And we know that there is also a phase transition for our version of the whole plane. But we know also that if we take Q equal to P, we should recover the standard Belleville spectrum. So we know a few things. And so I just here recollect what is known about the average integral mean spectrum of SLE kappa, which you have seen before. So the beta 0 of P, the beta linear of P, which I've shown before, with the transition point at this value P0 star. And then, as I mentioned, there is a tip integral mean spectrum, which is given by this closed form here for P less than -1 - 3 kappa over 8. Okay, so you have the tip version, then you go up, you have the beta 0, and then you have the linear part. This is for on the line P Q equals 0, so any P. P negative, you go through P equals 0, and then you go up to infinity. Now, the claim is that when you look at the whole plane SLE kappa generalized integral mean spectrum, there is another function which pops out, which is given by this one. So, which is the same as before, except that now it depends on Q2. Remember, we had it in green before. This was this function. Sorry, this function depending only on P. Now there is another one which depends on Q, which is very similar, which is this one. And of course, if you take Q equals 0, you get the former one. So we have this function now depending on P and Q, and the question is, which we get out of of course the study of the differential operator corresponding to the mixed moments, and the question is how to match all of these possible spectra, because this is value for Q equals 0. Of course, for Q equals 0, we also know that there is a phase transition at P star where you have the beta 1 for Q equals 0, and then we have to match everybody. Okay, so the naive way to start with is just to look, you have these 3 functions, and to look at 4 functions, sorry, and to look at in the PQ plane, where do they match, whether they match or not, okay? So you do that, and you play a little bit, and then your parabola pop out, actually. So I don't know if I should really, bring you with the whole details, but remember we had this parabola. So this, I said this is a red parabola. So this is red here. So it's for kappa equals 6. You have this nice red parabola, which is the one you saw before. So which is here also the same. So you have the red parabola. So I'm saying that along this parabola, the beta 0 corresponds to the beta 1, the new spectrum, the generalized spectrum, beta 1 of PQ, along this red parabola, only on this interval here. I should say something too, I forgot to say. Why do you have these two straight lines here, the vertical line here and the brown line here? They correspond to the domain of definition of your spectra. Because remember, the Smirnov spectrum cannot be higher than a certain value. You remember it disappeared at some point because it has a singularity in the square root. So this is this straight line here. So the Smirnov spectrum exists to the left, but not here. And so this is this straight line here. And also, you remember there was a transition from the linear, from the beta 0 to the linear spectrum, which is along this P here, P0 star here, this pink line here, purple line. So, so it looks a bit complicated, but you have, and also our spectrum here is defined provided this square root. So say you see here, this spectrum is defined provided P is less than the value which makes this vanish. And so here, the R spectrum will be defined provided this quantity, of course, is positive. And that tells you that you should be below a certain line, which is this brown line. So we can, our spectrum exists here, in this domain here, but not above. So this is why you have these sectors. Now, so the result here is that beta 0 will correspond to beta 1 on this red parabola for this, which was the one where we had exact results, right? So, which is on this part. And then there is another, actually, parabola, which we call green, which is this one here, which lives in this sector. So they bounce on those lines, okay? They nicely bounce on these lines. The red one, the green one here. So on the green one, you see here better. On the green, on this parabola, from this point here to minus infinity, on the left branch, you do have equality of beta 0 and beta 1. So it's not on the whole the green parabola, it's on from here to minus infinity. So if you want, you have these lines here where the R spectra and the Smirnov spectra coincide here, and you have also this part here, which is from here to here. And on the red one, we know exactly the result, so we are sure of the spectra here. Okay, so once you have this, you have somehow started to understand what could go on, and there is something else that you know that to the right of D naught, where you know that you go to the linear Smirnov spectrum, you know that your spectrum should be linear. So you have to see where this linear spectrum match the beta 1 spectrum, which is the new one, this one. So if you do this, you are going to find that they match along this blue line here, the D1 line. So you see, so there is a nice blue line here, starting from the intersection point of the green and the red parabola, which is here, where our spectrum matches with the linear spectrum. And here there is a line where the B0 becomes the linear spectrum. And here there is a part where they do match too. So actually, if you look at the transition point we were seeing for Q equals 0 before, it is here. Okay? Remember I said you go from the Smirnov spectrum to the standard spectrum of the bulk SLE to the new spectrum. That was at a certain P star. That corresponds to Q equals 0, of course. So that corresponds to that point here on the green parabola. Okay, now of course you have to look at the tip spectrum. So sorry, the tip spectrum is here. So you have another, so you have to, so this is the same red parabola, same green parabola, but then you have a quartic somewhere, which is this blue quartic, where actually the beta tip corresponds to the merges with beta 1. And they don't merge on the whole quartic. There is another branch to the quartic, but not on whole this curve, but only from here to the point Q0 and below. But of course, the tip spectrum is relevant only to the left of this value P, of P here. So it means all of these parts here do not matter. So what matters is that what happens to the left of this line here, and to the left you see that your blue quartic here intersects nicely here, there is a triple point, where the green parabola intersects the blue quartic, and after that, this would be our spectrum, the green one, merging with the the standard bulk spectrum. But here, along the blue one here, our spectrum, the beta 1, merges with the beta tip. So clearly the candidates will be along these lines and then the blue line. And the red one here was a kind of decoration where we have exact results. And then we have this line. So the upshot is the following diagram. So you have here, this is a tip transition line here. And this is a transition to the linear spectrum here for the bulk SLE spectrum, whole plane SLE spectrum. This is a tip transition. So this here you have the beta tip. This is a branch, a part of our green parabola. This is a famous line of slope 1 where the linear spectrum becomes our spectrum, and this is our new spectrum. So this is a linear, this is linear, this is a part of a parabola, this is a part of a quartic. And so the claim is that you will have beta tip, standard bulk SLE spectrum, standard average linear spectrum, and here this whole plane. And so here they depend only on P, of course, and here they depend on P and Q. And the nice thing that if you look at now, you remember I said that when you take this is for the inner version of the whole plane, mapping from the interior of the disk to the exterior. But if you do an inversion, you get the exterior map, as I explained. So it means, and I explained that it was corresponds to Q equal 2P, right? So Q equal 2P corresponds, you can't see it, but it corresponds to the light blue line, which is here. And that line never goes into the domain. So you see, because it would cross the green parabola further down here, but before that there is a quartic, and then it stays away from the quartic. So, and that corresponds to the version of the bulk SLE, the whole plane SLE, considered in the work by Belayev and Smirnov. So that line actually never intersects the domain. And that's the only one actually, because this red parabola where you have exact results has a slope which is exactly 1. So there is one line which is intersects only once. That's exactly Q equal to P. It's slope 2, so Q equal to P. So any other version would have exact closed forms, and this one doesn't. And so if you look at the M-fold spectra, it's kind of nice because you can take P equals 0, and then, as I said before, you have this result that the M-fold spectrum is the M equal 1 spectrum for QM, which is a deformation of P and Q, a thin deformation. But if I take Q equals 0 for the standard spectrum of the M-fold, I have a QM which is running like this. So if I take M negative enough, meaning, making the M-fold and taking an inversion, I'm going to have, stars with, these M-folds are just copies, but when you invert them, they become stars. And when you use these stars with M big enough, you are going to see some new phenomena, and which is exactly what is here. That is for the aficionados. So if you take P equals 0, so Q equals this, M large enough negative, M equals minus 30 for kappa equal 2, you are going to have this core line here, which intersects our domains 3 times. So here you have the tip spectrum, here you have the standard bulk spectrum, here you enter the new domain where it depends on P and Q, and then you start again and you intersect again, then you are going to end up in the linear domain of the average bulk spectrum. And just to finish, of course there is a question of what is the universal generalized spectrum. There was a question today about this, about the universal spectrum. And so because we have the domain, remember, we have this kind of partition of the plane for the SLE kappa. So the question is what happens in general for all the maps, inequivalent maps. So of course here we have used all the known conjectures which are far from being proven, or nobody is really sure whether they are true. So so the claim would be that in some domains that will be the universal spectrum for the mixed, and that we can prove in part of this domain. At some point here you will have a straight line where you go to the P minus 1, which is known to be correct, and then there is here a crossover there is a green line here, which here has been drawn as P square over 4, which is a Kretzer conjecture, saying that the supremum of all the universal these integral mean spectra should be p squared over 4, but in general there is a certain function beta 0 of p bar, right? A certain function. So that should match. So where this function and this one match should give you the new domain here. So we certainly believe that this is correct because we can actually prove it for p positive and underneath that curve at some point, for a certain domain underneath that curve which goes to -1/2. And you can also prove the validity of p minus 1 here. And of course it's not known whether the transition from the universal spectrum, which is maybe p squared over 4, to minus p minus 1, it is known that for p negative enough, it should be minus p minus 1. And it is conjectured to be at p equal -2, where it's conjectured that the value of beta is actually 1, which is a Brennan's conjecture, which actually is included in Kret conjecture. So if you believe all these conjectures, that should be the universal spectrum for. But if you don't believe in the Kret conjecture, you just replace this green line by the matching of the universal spectrum with this function. So that's it. Thank you. Yes.
So, is there any hope that you could get results for more general Levy processes other than
for this for the general moment?
sort of results in the spirit?
Well, yes, I think so. Yeah, yeah, certainly, yes. Yes, for the general, you mean the closed form results?
Yeah.
Yes, I think so. Yeah, certainly, yeah. Because, yeah, that's the same, we have the equation and we just change the generator, but somehow the properties go through, yes. So, part of the properties, yes. It will be just, yes, very similar. Yeah. The same way it was done in the first paper. Yeah. Yeah. Too many spectra.
Okay, then let's thank all the speakers of today.